My recording medium, unfortunately, sucks. But, right now I'm going to do, or like, show how to do, the heat equation with non-zero temperature boundaries. Because it's not particularly realistic that the temperature at both ends of like a stick or something is 0. Yes, that's actually kind of ridiculous. But anyway, and so the heat equation is usually written in this form. So the derivative of u with respect to time, or I'm just going to say that u is the one that is in terms of x and t, equals k or some other constant times the second derivative with respect to x. And remember that it can always be written again as this, which is normally how I like to write it because it's less writing. And so I'm just going to say that the initial conditions are some f of x. You've probably seen this too, and that you have the two ends, since we're choosing ones that are more realistic. Say u1, u2. Or if we're talking about the heat equation, we might as well call them temperatures. So I'll call this T1 with a capital T. And T2. And so the first thing that I would recommend doing is, or rather, the first thing that you would probably want to do. This is actually a fairly simple heat equation, there's nothing else. Is you want to solve for what's called the steady state. And so the steady state basically means that the time derivative is 0. And that's just because it doesn't have a time derivative. You see the steady state, it's usually abbreviated with an S. Or some people, I think they call it like the equilibrium state. It's all the same thing. This is only in terms of x, the positions, not in terms of time. Hence why it's steady. So u sub s of x, if we're doing steady states, then we have k times u. Oh, I did not make this convenient for myself. From now on, we're talking about u of s. X is equal to 0. And so, from this, you can probably guess if it's in respect to that. We know that if we take two derivatives, then we get to 0. I don't know why I did this. The time derivative, that's not u, that's 0. Because if the time derivative is 0, then our original equation becomes 0 is equal to k times the second derivative with respect to x. And so, if we look at this, then we can see that if u, and the k is insignificant, if u with the second derivative of u with respect to x is equal to 0, then I don't know how obvious this is, but it's going to be in this form. And why is this the case? Because if you take the first derivative, then you end up with a. And you take the second derivative, then you end up with 0, which aligns directly. So it's essentially a linear solution. Now this is only the case of like, it is this kind of simple heat equation. And so if we plug this in, we got u of, so we know that given the boundary conditions, which are these, the initial condition refers to where it starts in at time 0. The boundary conditions are basically irrespective time, so when it hits a certain value on the x spectrum, what it equals. We know that u of 0 is equal to t1, so we write that, and sum L is equal to t2. So if we plug this in, then we get A times T1 plus B. And we get, this is not right. If we plug this in, I'm sorry, it's equal to A times 0 plus B is equal to T1. And this one is equal to A times L plus B is equal to T2. Sorry about that mix-up. So then, if we solve easily, this goes away. B is equal to T1, we see. And USAL plus B is equal to T2. So if we plug in for what we solved here, then we can put in T1 is equal to T2, and we get that A is equal to T2 minus T1 over L. And so then our equation becomes, we know that our steady state solution is now equal to T sub 2 minus T sub 1 over L plus our B, which is T sub 1. And so what does this actually mean? And this, for a while, did not make sense to me. But it basically has to do with the fact that now that we've solved for a steady state, we can, and the steady state is always going to be equal to, it'd be true, what is true of the steady state is this equation, which is U where U sub D is the Dirichlet, and I don't think I can spell, but I will try. Dirichlet solution. And so it's going to be, we can solve, fortunately for us, it's not extremely difficult, but if we solve through the derivatives, we could now solve it again with those values and get what we wanted. Although that was really unspecific. I apologize. So, in some places they'll call it V of t, or they just call it U of d. And so what's true of it is that we can just take, if we take the derivative of this, then we get the partial derivative with respect to t of u is equal to us t plus u t. And since we know that this is going to be 0, then we just get this. And we also know if we take the other side, we have this. Oops. Which is then equal to just the Dirichlet. Oops, yeah, okay. And so from there we know that this must also satisfy the same conditions. And so we get is equal to u of d is equal to u of x. So if we plug this in again, minus whatever the standard state was. And this was previously defined as the initial condition right there. So then we can even simplify this further. X. And let's remind ourselves that the standard state is only in terms of x. And so if we solve these conditions out, we have these. And this is true because if we take the original equation, yes, that made sense. The full U minus the standard state for the value of x is equal to L and x is equal to U, no, x is equal to U, x is equal to 0 and x is equal to L are equivalent. So essentially, this is true. Because this is true, then we can say that this is true, which then just brings us to our normal homogeneous equation, which is what we wanted. And so if we solve that out, as you'd imagine, so then we have the same equation again. Oops, this is an x. This is what happens when you're using notes. QD. And we found earlier that this is equal to f of x, which is the initial condition minus the standard state, which is also in terms of x. That we'll write to remind ourselves that. And then we have our conditions here, and I'm just not going to rewrite that. So this is solvable, well, as you might see. And what we'd get from this is a separation of variables. So if you do this separation of variables, and I'm not going to write it all out because, frankly, that's very troublesome. But this will yield you your separation of variables, and so you end up with the Dirichlet solution, which is in both, is equal to your good old Fourier. And this is, so this comes from, if you remember from separation of variables, where we had it equal to this. So we have, this is a problem, is equal to t. And then we divide and we get t. Equals, I already used k, so let's use alpha, or kappa. I already used kappa, so let's use alpha. And so we get that, and so if you solve out the t, then you'll get the exponential term here. So that's where the exponential term comes from. It comes from the separation of variables. And then the sine term and the n pi x comes from the fact that when you do the x term, you get C2. That. And so if you put in the boundary conditions again, you would get that in order for this not to be trivial, you would need to make this equal to 0, which then gets us our conditions of n pi over L. And so how we got Bn is going to be contingent upon the, so if you write out the t, you actually find out it's equal to this. This was, I might as well keep this consistent. This is alpha. Sorry, I messed up the variables. It's this. this looks familiar. Yeah, so it all comes from the same place. And then if we solve this, and this is just using orthogonality of signs, then we get this mess, which is 2 times the length x minus the standard state. So this is our new, I like to call this a new f of x, or I call it like g of x. So when you normally look at the formula, and the formula is normally this. This is the one that I always memorize, so I know what I'm doing. And then this, where n is some integer value. And so the reason why I don't have a denominator, and I almost always write a denominator, is because if this is normalized, then this is just equal to 1, and it doesn't matter. And so if we write out our full answer, which is the standard state plus the Dirichlet, we get this giant mess of the standard state that we got before, plus the d sub n, and I could write it all over again, but that's a waste of ink and paper, times height of k and pi squared Lt. By the way, I forgot to do it in this one, but I lost the k somewhere, so it was originally here. So I would move this over, so I have 1 over k, which would then give me the k from before. Yeah. Okay, so that's how you do it. And so the steps are basically that you want to find a steady state if you have the n's are not equal. If I find my paper. If the n's are not equal, you want to find a steady state. And then the steady state allows you to find the Dirichlet, which is then standard separation of variables. And then you can just use orthogonality and solve it like normal. Okay, thank you for listening.